There we go. All right. So what did you guys think of this chapter? Did you like it or no?
No.
No. You like the
This
rhythm?
chapter was harder, I think, than the previous ones, maybe.
See, for me, I thought it was easier.
I think calculus is hard just in general.
It is hard in general, for sure. I agree with that.
That's
I thought
true.
this chapter was better, except for the last two sections I'm still kind of struggling with.
The integrals where you end up with an ln, or where you end up with the inverse trig function, those.
Yeah.
Okay. Yeah, those are kind of can be a little tricky because like there's not a whole lot of difference between formats, I guess, so you really have to know what you're looking for. So yeah, those can be a struggle.
Yeah, I was struggling kind of like later on, maybe if we have time, but on the study guide, they have those, you have like 3 of them that are really similar.
Mm-hmm.
And so, but they're all like a little bit different once you solve it. So some are the LNs or some are the other ones. So I don't know if we could go through those ones later. I think it was like 1, J, K, and L.
Okay, yeah, we can definitely do those. Yeah, so that's kind of along in the vein of what I wanted to do. I also wanted to go over like the second fundamental theorem of calculus, just a little bit, because it's easy to forget, and it's one of the most commonly missed questions. Just because people kind of gloss over it, and then they see it and then they forget how it goes. And kind of like some definite integrals, what they do, and then we can just kind of go from there. Okay, so let's get the second fundamental theorem of calculus out of the way. Do you remember what that did? Or what it allows you to do?
Does it give you a shortcut to find a definite integral?
It gives you a shortcut to find the derivative of a definite integral, yeah. So like if f of x is equal to the integral from 3 to x of the square root of ln of t minus 1 dt, then the derivative would equal, and then it would ask you, okay, well, what's the derivative? So you have two options. One of them is to actually try to integrate this and then plug in the bounds. And then after you do that, then you would take the derivative of the result, because that would, once you integrate, plug in the bounds, that's still just f of x. So you would still have to take the derivative. But a lot of times you have this crazy looking function that you have no idea how to integrate that. So instead, you can use the second fundamental theorem of calculus, which just says, hey, if you're going to integrate and then take the derivative, wouldn't you just end up right back where you started? And the answer is yes, you do. You just kind of go in a circle. And all you need to do is just take the t and replace it with this x, and you're done. So this would be your answer. So it's a really nice theorem because it shortcuts a lot of stuff, and it's like a 3-second question. However, there are some nuances to it. So most people remember this. It's when they have something like this one, they're going, what? So let's change it from the integral from 3 to x squared. So when the bound is no longer just x, like it's x squared or x to the third, sine of x, could be 4x, something like that, then you have to use the chain rule. But you can still use the second fundamental theorem to shortcut and then just kind of throw in the chain rule at the end. So you're still going to do the same thing as we did before. You're still going to take the t and replace it with that variable that's up there. So in this case, it'll be ln of x squared minus 1. But then with the chain rule, you know, you have to make sure that the derivative of everything is accounted for, including the derivative of that bound up there. So you need to multiply the entire thing by the derivative of this x squared, which would be 2x. And that would be your ending derivative. So it can be a little tricky when the upper bound isn't just an x, then you just have to be a little careful about, you know, what you have and what you're doing. But I just thought I'd go over that because, again, it's missed quite often, or whenever there's a second fundamental theorem question. Okay, so do you guys have any questions on this? Is it all good?
Yeah, it helps clear it up a little bit, seeing like the two different ways.
Okay, cool. Okay. All right, let's go ahead and talk about those questions that you asked about earlier. You said it was I, J, and K off the study guide?
J, K, and L.
J, K, and L, okay. Oh, and I don't have the study guide pulled up. Could you tell me what J is?
Sure, so it's the integral of negative 8x over the square root of 5 minus 4x squared dx.
Okay.
That's the square. J is with a square root of on the bottom.
Oh, it's the square root. Okay.
Yeah.
Okay, so like that.
Yeah.
Okay. And
And
K?
then K is just it's the same, but it's just negative 8 over the square root of 5 minus 4x squared dx.
It's still on the square root?
Yeah.
Okay, and then L?
Then L is negative 8x and then over 5 minus 4x squared dx, no square root.
Okay. So when you're integrating and there's a fraction, there's one thing that I will always do first, and I will look at whatever's in the denominator and just check it really quick and say, okay, is the derivative of the denominator sitting up top? And if the answer is yes, then you're pretty much done. It just defaults right into an ln. If the answer is no, then you can start to kind of go through some other options. So if you're looking for like, okay, what do I do first? Like, I would check the ln, see if that works. If not, then you can, it's kind of a toss up to what you want to check next. You could check inverse trig. And then the third thing that you can check is the U sub. The second and the third one, that can alternate, and whichever one's your favorite. But I always check that first one. Just check the ln, because it's usually pretty easy to do, pretty quick, and it's usually obvious when you don't have the derivative of the denominator. So out of these three, which one of them has the derivative sitting on top?
J does.
J does
No,
not.
it would be L.
Oh, J doesn't.
No.
actually.
J, you have the square root of 5 minus 4x squared.
Mhm.
So you have to, the square root's down there, so it's still part of that function.
Got it.
So the derivative of that square root is going to give you another square root. So it's not up there, but it is with L. So since it's L, you can just default it to ln of absolute value. 5 minus 4x squared. And then what needs to come next?
Plus C.
Plus C. Yeah, if it's not a definite integral, don't forget about the plus C.
So quick question.
Yeah.
So I'm looking at 5.8, the inverse trig functions. And couldn't you use one of the couldn't you use one of the formulas, or one of the for L?
No. Because you don't have a square root in the denominator. And you could, you might be able to if it was 5 plus 4x squared, because
Got
then it might try to fit an arctangent.
Got it. Yeah, if an arctangent, you're right.
Yeah. I know that's where it, like, they kind of get a little tricky because they have these little slight nuances that throws it.
Yeah, it's like the slightest thing can change everything.
Yeah. It really can. So that's why if you kind of have a list and like, okay, check the ln. All right, checked it. All right, let's check the inverse trig function. Okay, it's not those. Let's just check a U sub. And just kind of go through that, and that helps a little bit. Okay, so L is done. All right, which between the two, between J and K, which one do you think is the inverse trig function? If you haven't looked at the answer key.
J.
Okay, so for inverse trig function, since you have a square root of 5 minus 4x squared, would you want to go with arc sine or arc secant?
Arc sine.
Arc sine. Okay. So this is
We're
the
solving.
formula for it.
Are we solving J or K right now? We're solving J, right?
Yep. That's when you said, right? That's the one you picked.
Yeah, I said J.
Okay. So you need the derivative of the U to be on top. You don't want the derivative of U squared. Does that make sense?
Yeah, so it would be K.
So it's K. Yeah, so like your A squared is 5, your U squared is 4x. So that means the U is 2x, and your U prime is 2. Oh, excuse me. So you do have to kind of tweak it just a little bit. Because you want a 2 up there, not a -8. So there are a couple of ways to deal with that. So what do you guys want to do? How would you handle this -8 that's inside?
So multiply by -4 and then 1/4 on the outside.
Okay, yeah, you can do that. You could just pull off a -4 if you
Okay.
wanted. Or do exactly what you said, either way. Because you'll end up with the same exact thing no matter which way you go. Okay, so now you have the right format. You have a squared minus u squared underneath inside the root. You have the u prime sitting on top. So now it's just going to go right into the formula. Oops. Got the -4. So -4 inverse sine or arc sine. The u, which was 2x, all over the a, which would be 2 root, or just root 5. And you can rationalize it if you want to. But you don't need to.
Quick
Okay,
question.
so yeah,
So if, how come choose the numerator? Oh, because it's u prime. So we're just plugging it in.
yeah.
Got it.
So you either split off you either pull off the -4 to make it a 2, or multiply the inside by, or the outside by -4, inside by 1/4. Or -1/4, and that's how you can do it. Either way you want to go. All right, so for J, it's not an ln, it's not the inverse trig function. So chances are it's just a u sub. So what would you choose for the u?
For J, I would choose the 4x squared.
That's close. There's a little more that you want to choose.
Wait, for J.
Yep.
Because if I did the derivative of u, I would get 8x, and if I do d, I'll get du equals 8x times dx. Don't you have 8x in the numerator?
You do. But it would look like this once you did it. Which, I mean, you can do it, but now you still have to do another u sub. You'd have to do like a w sub,
Got it.
because you've got this 5 minus u. So you're on the right track. It's almost there, but you didn't pick everything that you want to.
So what's a better option to use?
Everything that's inside.
So everything, so 5, the whole 5 minus 4x
Yep.
squared.
Mhm. When you pick the u, you typically are taking everything that's inside the radical, everything that's inside the parentheses, everything that's inside the angle, everything inside the ln. You most of the time you don't pick like a term out of there, or a couple of terms. You just go with the whole thing.
Because I
So
was looking at,
that's
'cause I was
that's
looking
for
at
the
some of
use.
past ones. I was looking at some of the past ones, and it's like where you just pull out like instead of you would put for you would pull out like the 4x squared, and take the derivative of that.
That was because, are you talking about like for K?
Yeah.
That's not, that's because it's not a u sub.
Is that use because there's a 8x in the numerator.
Hmm.
Got it.
Yeah, and same with L. This is fitting the L. You could technically do a U sub as well, and it just kind of bumps you back into an ln. But there's, I mean, if the derivative of the denominator is on top, it's just automatically an ln, and then you don't have to do U sub to get there.
Got it.
This one you do. Okay, so now you've got the right du, you've got the right u, so you can start plugging in everything. So flip or change the radical into an exponent and then flip it up. And then when you integrate with the power rule, you add 1 to the exponent because it's the opposite of the derivative. So -1/2 plus 1 is a half. And then you can multiply by the reciprocal of the exponent, which should be 2. And then plus the c. And then change everything back into terms of x. Okay, so does that help kind of clarify what you're supposed to do for those?
Yeah.
Yeah, that made it a lot easier
Okay,
to kind of see it. So just to repeat though, so for K, we said that that was the derivative, and that's just because U doesn't have the X, right? Is that kind of what we were looking at? Like why the derivative, like on top, why it becomes the arc sign?
yeah, because for your arc sine, arctangent, arcsecant, it's always the u prime. It's not the derivative of the actual term itself. You got to root it
Okay,
and then take the derivative and see if that's up there.
okay.
Okay, any other questions on these three? Okay. Let me talk about one that was on the last quiz. And there are a couple of versions of it. So let's do this one, 1 over x to the third dx going from 1 to 2. The other version was 1 over x squared. But either way, you would do it the same way. I saw a lot of people trying to do a u sub with this, and it was really interesting because they were trying to go like u is equal to, and I saw several people like set u equal to a number. Well, if you did that, what would your du equal? Like, what's the derivative of 2?
0.
0. And you don't want 0, you want a 1. So that should automatically tell you, whoops, can't do that. If it's going to be a u sub, you're going to be choosing some sort of a quantity for x. It's usually just not like a single term like x to the third or just x itself. So if it's ever just an x down there with an exponent, all you do is just flip it and change the sign on the exponent. So it's just x to the negative third. And now it's just a power rule. So add 1 to your exponent, multiplied by the reciprocal of your exponent. And then you're going from 1 to 2. And for myself, if there's a constant out in front like that, I usually just pull it out to the front. And then I plug in the bounds. You don't have to do that. You can keep the -1/2 attached to it. It just depends on what you want to do. And then the other thing I saw too is people were plugging in the bounds backwards. So their answer was coming out opposite in sign from what it was supposed to do. So you always plug in the top bound, even if it's the smaller one of the two, just whatever's on top, plug it in first. And then minus, take the bottom number, no matter what it is, and stick that in. And then just start to evaluate it. So 2 to the -2 is just a fourth. 1 to the -2 is 1. And then a fourth minus 1, -3/4. Finally give you 3/8.
You said problems on what quiz before?
11,
11.
so the
Okay.
one that was last week.
Okay. Because I want to see. I want to see how I solved it, just so I can compare. Oh, I see it. Wait, is every quiz different for everyone, or is it the same?
The concepts are the same. The actual problems can vary.
Okay, that's okay. Maybe that's why it's different. Maybe that's why it's different for me.
Yeah, so there's a little variation in there. So Canvas has like a bank of
Got
questions
it.
that it's choosing from. So I don't have control over which one it assigns to you. I have control about what gets put into the bank, but it picks one to give to you.
Got it. So maybe that's why mine. That's why I didn't get something like that on my quiz. That's why.
Well, yeah, because you probably had the 1/x².
Yeah.
Yeah. So if your function is different, your answer should usually be different.
Mhm.
Most of the time. All right. All right, what does a definite integral represent?
Does a definite integral represent the area under a curve between some x values?
Yep.
Yay.
Yeah, exactly right. The area under the curve. From x equals a to x equals b. And the x-axis. So anytime you've got the integral of a to b, oops, the definite integral of a to b of f of x dx, it's taking the area from a to b, and if it's above the x-axis, that's always like a positive. And if it's below the x-axis, that would always be What kind of a value?
-1.
A negative. So it's possible for these things to come out negative, which is okay. Like, don't assume like, oh my gosh, I did it wrong. It is possible to come out negative. It's just kind of, it's giving you like a net area. So if it comes out negative, it's just saying, hey, most of the actual area is underneath the x-axis. So let's say you came across a definite integral and it wanted you to evaluate it, but it does not fit a u sub or any other integration technique that you know. How would you evaluate it? I guess not a u sub, doesn't fit an ln, doesn't fit any of the inverse trig functions. You don't have a formula that's been discussed in the class, but it still wants to know what it equals. So how would you do it? Or what could you do to figure it out?
Would you, I don't know, but would you use Riemann sums or like the limit process?
You could, but chances are that's going to make it worse. Because usually if you don't know how to integrate it, it's some complex thing that if you started to stick it into the Riemann sums and do the limit stuff, it's just going to be a bear. And you wouldn't
would
have
this-
any summation formulas that would work with it either.
Would this just be the first fundamental theorem of calculus, the f of b minus f of a?
If you could integrate it, sure.
Oh,
but
that's it. Okay.
yeah, like if you can't integrate it and you don't know how, and the limit definition isn't working either, what's your only other option? And it's something that we did kind of early on in the chapter, mainly I think 5.3. But it's something that hasn't been done for a while. So, I mean, it's easy to forget. And it goes along the lines of this question that we just did before. You know, what does a definite integral represent?
Well, I think in 5.3 we did we found like the area under a curve, like total area, like if we had two shapes, and also like the value of definite integrals. So is that what we're getting at? Maybe shapes?
Mm-hmm. Yeah, if you can't integrate it by any known integration techniques, and the limit definition isn't working either, and I would only use that limit definition if it told me to. Then your only other option to try is to actually get a graph and figure out the area that's under the curve, because it might actually be a geometric shape. Because if it comes out like, you know, as a rectangle, then you just have the area of the rectangle, or a triangle, or I don't know how it would do it, but if it was a trapezoid, you could use the area of a trapezoid, and so on and so forth. But just always kind of keep in mind, you know, every time you see a definite integral, you know, just what does it actually represent? Just kind of keep that in there. If it wants you to evaluate some stuff and you're going, wait, how do I do that? Like sometimes it's not just an integration technique. You have to go back to what it represents to kind of go, oh, wait a minute, I could just do this. And Sometimes if you graph it, it comes out and for an answer in like 15 seconds. Oops. Okay, let's see, what other questions do you guys have? Either from the study guide or just whatever.
I had a question on number 10. On
From
the study guide. Yeah, so I solved most of it. I just couldn't figure out the last part. I forgot how to set it up.
Okay. Here, let me just pull it. Number 10.
Yeah, so like specifically 10C.
Oh.
It's probably not as hard as I'm making it, but
I think I have a different. Okay. Oh, okay. All right, here we go. Okay, so R is the region by the bound of those graphs, sketch the region, find the area, and then, oh, so there's part C, where it divides it into 2 equal halves.
yeah.
Okay. Okay, so for B, you figured that one out?
I did, yeah.
Okay, so what did you get for the area? Because we'll need that value.
So B, that would be, I got 1.
1.
Yeah,
All right, so what you do, so let me draw it out just so you can see it. Oops, that was sine. Okay, so pi over 2 is that first intercept. So this was your region, that was R. So what it's saying is like, okay, you have the line x equals k. And it's split the region into equal halves. So if the whole region is 1, then this side has an area of a half, and then this side has an area of a half.
uh-huh,
So you can set up one of 2 integrals. And the one I would go with is the integral that has a 0 in it. So if I integrated from 0 to k of the function, the same function, that cosine of x,
uh-huh.
I know that the answer has to be a half. And so now you have an equation that you can actually start to work through.
Oh, that makes, okay, yeah,
So it's going to be pretty much almost the exact same steps as you did in the first part or in part B.
uh-huh,
I mean, you integrate it and you still get sine. But now you're going from 0 to k, which is all right. Like you can have the variable be a bound. So you still plug it in. So sine of k minus sine of 0. And then it's still equal to a half. And then sine of 0 is still 0. And now you're just solving for where sine is equal to a half.
Oh, okay, I get it now.
Okay,
Yeah, so
Um,
pi over 6.
yeah.
Yeah,
And for this one, there's actually a second answer for sine where sine of k equals a half. Because it could be pi over 6 or 5 pi over 6. But you can't choose the 5 pi over 6 because that would be over here. So you have to go with that one.
okay, yeah, that makes sense.
Okay, the other integral that you could set up as well is if you went from k to pi over 2. You could set up this one because then you, instead of doing this side, you'd be doing this side, which is fine. I just like to have 0 as a bound because it usually knocks a term out. But you can do either one.
Okay, cool. Yeah, I
Right.
have another question, but if anybody else has any other questions, they can ask.
Nah.
Uh,
All right, go for it.
Okay, well, number 6, because we haven't done anything. I don't feel like we did any problems in the examples, like in the notes.
Okay, t equals 0. Yes, it's like we kind of you did. It's just in pieces.
Oh, okay.
Okay, so it starts at 6, moves along the line in such a way its acceleration 24t, the particle's velocity. What is the position? Okay, so we know two things. You know the position of the particle when t is 0, or we know 3 things. We also know the velocity when t equals 0, and we know the actual acceleration function. And I think this is kind of, I think this is similar to the homework questions too. So we know the acceleration is 24t squared. So if you're starting with acceleration, how would you start to get to position?
Take the antiderivative of the function.
Yeah. So we're going to integrate it. And that will get you to velocity. So if you integrated 24t squared, what would you end up with?
Eight t to the 3rd
Yeah,
plus c.
plus your c. And so now you can use that other given piece of information that the velocity is 8 when t is 0. So you can plug in 0 for t. And set it equal to the velocity, which was 8. So the 0 knocks out that term. And so c is going to equal 8. So now you have a velocity function. So 8 t to the 3rd plus 8. So to get from velocity to position, you're going to have to integrate again. So now you're going to integrate 8t to the 3rd plus 8. So that would be 2t to the 4th plus 8 t and then plus another constant. And now you can use that last piece of information. So when t was equal to 0, where'd it go? The position was at 6. So c has to equal 6. Oops. So there's your position function. And then you can finally answer the question that they're asking. What is the position when the particle is at t equals 2? So stick the 2 in there. So 2 to the 4th, 16. 2 times 8 is 16. And then still plus 6. Okay, so 2 times 16, 32. 32 plus 16 is
48,
48 plus 6,
54.
54. And because there are units in the question, you need to also give units in the answer. So it's 54 what?
Feet per second.
Close. That would be a velocity. But if it's position, then there's no time unit. So it would just be just feet. So velocity is always the length over time. Acceleration is always the length over time squared.
Quick question.
Yeah,
So where you crossed out s of t, is that 2t to what power?
the fourth.
The fourth.
It's
Okay.
the same function here.
Oh, got it. Okay. And then define t. How'd you find t again?
The two.
Yeah.
That was from the problem. So what is the position of the particle at t equals 2? Yeah.
Got it. Can you go over 9?
Sure. Okay, which of the following properties are true? Okay, so the first one. A to B k times f of x dx, it's saying that's the same as k times the integral from a to b of f of x dx. So what it's saying is, hey, if you have a constant in there, are you allowed to pull the constant out? So are you allowed to do that? Could you take this 4 and pull it out?
Let me see. Yes.
Yeah, so that would make this first one true. Okay, and then the second one is really similar. So if you have x times f of x dx, can you pull the x out? Or
You can't because it's not a constant.
right. So you ever find yourself either pulling a variable to the front or multiplying the outside by a variable, you better stop because you're not allowed to do that. it might make what you're doing very simple, but it's going to make it very wrong if you do. Okay, then the third one from A to B, f of x, is that equal to integral from A to C plus integral from C to B, where C is in between or somewhere between A and B. So are you allowed to take a definite interval and split it into two?
That is a good question. I'm gonna say no.
You actually can.
You can.
Yeah.
What's the reason? why?
That was like what you did in number 4. So you can take any definite integral and split it as long as where you're splitting it is somewhere between the bounds.
Is there ever a point where we're gonna want to split that, like when solving integrals, or not right now?
Not necessarily right now, but eventually, yes. Yeah, so for now, it's more of just kind of that you can do it, and that end you can apply it. So like if you went from, I don't know, 4 to 10, you could bust it apart and go from 4 to 5. And then do the rest of it from 5 to 10. You're totally allowed to do that. So that's what you have to do in number 4. There's also a quiz question on it, and I think a few homework problems on it too. I think we did it in the notes. Where it gets practical in this class is like you had a whole graph of like a bunch of different shapes kind of all stuck together. Like you had a triangle, and then a circle, and then like another triangle, and then like a rectangle or something. And it was going from A to B. We did we kind of broke it apart into sections, like we went from A to 0, A or 0 to wherever, and then that number to B. And then it wanted the whole thing because you're just adding up the individual areas. So that's all of this is saying. Because you can also go backwards. You can take the whole area and then split it and find just different sections of it. Okay. Let's see. Do you have any others that you want to talk about? I think I've got a couple more minutes.
Can we do 1Q?
1Q. Sure. Yes. So this e to the 2x, we've run into it a few times before. E to the 2x you can either rewrite it or think of it as e to the x squared. Because when it's written this way, like you just multiply the exponents together and that's how you get the 2x. Well, you can always go backwards. So this is really e to the x squared. So you can run through your checklist again. You can check the ln, you can check the inverse trig functions, or you can check the u sub. So the derivative of the denominator is not up there. It's close, but it's off enough to where it's not the ln. So then for your inverse trig, your a squared is 4, your u squared is e to the 2x, which means the u would be what?
Just e to the x.
E to the x. So the u prime is still just e to the x. So this one actually works. It is an inverse trig function. And since there's no square root down there, that's going to make it the inverse tangent. So 1 over a, so your a squared is 4, so a is 2. And then inverse tangent of u over a, so e to the x all over 2, going from 0 to 1. Again, I'll just stick that half on the outside. So I'll plug in the 1. And then minus, plug in the 0. And that's about as far as you can take it, because there isn't anything on the circle that matches to that, especially the e over 2.
Cool, thank you. Changing it to the x squared, you're squaring it, that made
This,
a lot of sense. Yeah.
yeah. I know when I first started encountering it, I was like, whoa, what? So then I was just like, oh yeah, it's just it's just that. Okay, well, that's about all the time I have for today. That went by fast.
Thanks for the session.
Oh, you're welcome.
Yeah, thank you.
If you still have questions, just send them to me, and I'll be able to answer them.
Awesome. Will there be another review session for the final?
Uh-huh. Yeah, it'll be next Thursday. So a week from today.
Awesome. I'll see you then.
Okay.
Yeah.
All right.
Thank
Thank you,
you.
Professor.
Thanks for coming, guys.
See you next week.
We'll see you later.